Okay, we're back with one more example of counting arguments. Okay, and this one is going to be about what's called a combination, where the order doesn't matter and repeats are not allowed. So this is similar to the permutation in the sense that we're choosing from, let's say, from a group of n objects, we're going to choose k of them. But again, like the permutation, repeats are not allowed, but what's different is this time the order doesn't matter. So let's look at an example. So the example that I usually like to start with is forming a committee. So let's say we have an organization with 25 members, and the organization wants to select a committee of 4 members. How many different committees are possible? Okay, how is this different than a selection of 4 officers? Well, notice that if it's 4 officers, then the order matters. So, but the order they're selected, first one selected as president, second one selected as vice president. If you switch them in the order, it's a different slate of officers. But if you're selecting 4 people on a committee for the same job, basically on the committee, then it doesn't matter which order you choose them. So we could start by thinking it in terms of the permutation. 25 permute 4. That's 25 times 24 times 23 times 22, or in other words, 25 factorial over 25 minus 4 factorial. That's 303,600 ways. However, that would be correct if the order mattered. But here the order doesn't matter. So what's happening is we've double counted or multiple times counted some of these. So, for example, if we're doing officers, John, Sam, Polly, Ashley as president, vice president, secretary, treasurer in that order is different than Sam, Polly, Ashley, John, which is president, vice president, secretary, treasurer. But the set, John, Sam, Polly, and Ashley, is the same as the set, Sam, Polly, Ashley, and John, which would be the same as if you're choosing them a committee. It really doesn't matter which one you choose first. They're either on the committee or they're not on the committee. So the permutation counts each committee member multiple times. So what we ended up needing to do is just find this permutation, but then we need to divide out by how many times we're double, triple, whatever, counting these committees. So how many ways are you recounting the same committee? Well, it's the same way. It's the same as the number of ways of ordering 4 individuals, which is just 4 factorial. So 25 choose. We're going to use the notation 25 choose 4 like this, NCK or 25C4, as 25 permute 4 divided by 4 factorial. So we can think of that, one way we can think of it as 25 factorial or 25 minus 4 factorial times 4 factorial. Or the 25 permute 4 is 25 times 24 times 23 times 22, but we want to divide that by 4 factorial, which is 4 times 3 times 2 times 1. Now, we can always, it turns out, interestingly enough, that this denominator is always going to cancel out. So 4 times 3 is 12, times 2 is actually 24. So there are actually 24 ways of reordering for, in this case, people. So each one, if we just did the permutation alone, I would count each of the committees 24 times. So I divide by that 24. That actually cancels this 24. So that 24 cancels with this 4, 3, and 2. And so that leaves 25 times 23 times 22 times 1, which is 12,650 ways. So there are always going to be more ways for the permutation than there is going to be for the combination for the same n and k. So let's see what we have here. Order doesn't matter. Repeats are not allowed, and we're counting the choices. So we're choosing from a set of n distinct objects. We choose an unordered set of k of these objects. N is a natural number, k is a whole number. K is less than or equal to n. Where we're choosing where repeats are not allowed, sometimes called choosing without replacement. And the number of choices is what we call n choose k. Okay, and that's defined to be n factorial over n minus k factorial times k factorial. Or another way to say it is just n permute k over k factorial. Sometimes this is called a combination. Sometimes it's called a binomial coefficient. And there's 4 different notations. The first 3 are the same that we use for permutations, except using a C instead of a P. But then there's also this last notation that's used by a lot of people. So if you see that on a homework problem or something, or out in the real world, out in the wild, that's a way of writing this so-called binomial coefficient or combination. I'll have a tendency really to use the first or third one here, mainly because they're the calculator notations for it. But let's start, before we get to a calculator, let's see if we can compute these without a calculator. So with what you've got here, let's see if you can go ahead and work these out. Get these worked out, press pause now. Okay, so 25, choose 3. If you think of the definition in terms of the factorials, it's 25 factorial over 25 minus 3 factorial times 3 factorial. Of course, this is 22 factorial, which cancels out the numerator, leaving only the first 3 factors, 25, 24, 23. So that numerator is the NP 25 permute 3, but then we have to divide by 3 factorial. See, 2 times 3 is 6, 24 divided by 6 is 4. So then we get 4 times 5 is 100, times 23 is 2,300. 27, choose 5. Here it is in factorials, but it really boils down to this. The first 5 factors here, starting with 27, going down by 1, 27, 26, 25, 24, 23, that's 5 factors. And then we have 5 factorial in the bottom. Well, let's see, I'm going to cancel the 5 with the 25 down to a 5. 4 times 3 is 12 times 2 is 24, so all that cancels 24 down to 1. And then I just have to multiply these out, which I could certainly do by hand or a little faster on the calculator. 27 times 26 times 5 times 23 is 80,730. And let's see what happens here for n choose 0. So it's n factorial over n minus 0 factorial times 0 factorial. Well, n minus 0 is n factorial, and the n factorial on the bottom and top, they cancel each other out. 0 factorial is 1, so you get 1 over 1 is 1. This should make sense. If we have n objects and we're not choosing any of them, how many ways can we do that? Well, one way. Don't choose anything. That's it. If you have n objects and you're choosing n of them, how many ways can you do that? Well, that also turns out to be one way. It works out in the factorial formula. N factorial over n minus n factorial times n factorial. N minus n is 0, so once again, you've got n factorial and n factorial top and bottom. Cancel each other out. 0 factorial is 1. And so that works out to be 1. Should make sense. If you've got n objects and you want to choose all of them, you don't care about the order you choose them, just putting them all together, well, you end up choosing everybody. So, only one way of doing that. If you have n objects and you choose one of them, how many ways can you do that? Well, n ways. You have the n different ones to choose from, you're only choosing one, so that's n. You can see it worked out here with the variables, with the factorials. N factorial over n minus 1 factorial times 1 factorial, because 1 factorial is 1. N factorial is n times n minus 1 factorial. Everything cancels except for the n. N choose 2. You got an n factorial, you got an n minus 2, and a 2 factorial. The n times n minus 1 times n minus 2 factorial on the top. The n minus 2 factorials cancel. So you get n times n minus 1 on the top, 2 factorials, 2 times 1, which is just 2. And so the answer is n times n minus 1, whole thing divided by 2. Now, luckily, just like the factorial and the permutation, the combination is built into your calculator. So in practice on tests and so forth, we'll probably just be using the calculator. So for TI-84 calculator, type the first number, then do NCR, type the second number. So you type the value of n, which is 25. Let's say do NCR, which is math. Left arrow to probability, and then choose number 3, which is NCR. 2 is NPR. 4 was factorial. Those are all found in the same place, basically. Then type in the 3, and that would be 2,300. In math notation, the 25 would be written as a subscript where the n is, and the 3 would be where the r is. On the Inspire, like the permutations, very similar. Go to the home screen there on the calculator screen. Press Menu, choose number 5, Probability, choose number 3, which is Combinations. It'll come up with NCR, open parentheses. You plug in, say, 27,5, close parentheses, and enter. This is 27, choose 5 is the way we would say that. Okay, so here's a problem for you. Suppose we're randomly drawing a hand of 5 cards from a standard deck. How many such hands are possible? See if you can figure this out. Well, if you're drawing a hand of 5 cards, you don't put it back to draw it out next. So the dealing is done without replacement, so repeats are not allowed. We're choosing K equals 5 cards from a set of N equals 52 distinct cards without replacement. The order doesn't matter. Once they're in your hand, you can reorder them if you want. The number of possible hands is 52, choose 5. So that's 52 times 50 times, 52 times 51 times 50 times 49 times 48. 5 factors there. Divided by 5 factorial, which is 5 times 4 times 3 times 2 times 1. That simplifies there. You can see some canceling going on. That turns out to be 2,598,960. Of course, the shortcut is just NCR on the calculator. Again, on the Inspire, it's Menu, number 5, Probability, number 3, Combination. Then enter the 52, comma the 5, close parentheses, and enter. And on the calculator that's TI-84 here, put in the first number of 52, then push the NCR, which is Math, and then left arrow to Probability, and then 5, and enter, and we get the same number. So let's review real fast before we go. So this is for counting choices where the order doesn't matter. Repeats are not allowed. We're choosing from a set of N distinct objects. We're choosing an unordered set of K of these objects. N is a natural number, K is a whole number less than or equal to N. Repeats are not allowed, so it's, in other words, it's done without replacement. The number of choices is N choose K, which you can see there, and you can see the multiple notations for it.